Hello everyone, my name is Krishna Raj and I am from VIT University and right now doing my MTech in CAD/CAM. Today I'm going to be talking about STL file, the introduction, the quality, how to determine its quality, how the data transfer is done, how it is repaired and how the layers are sliced. So this is basically the overview of my presentation. So I will be, as I told, I will be showing how the STL file quality is determined and what the interface between the CAD and rapid prototyping system is, the guidelines needed for data transfer, the data repairing, all the defects that are occurring in STL file, how they are repaired, that is the algorithm which is used, and I have also added two case studies in this presentation. So STL file, it is the short form for standard tessellation language and it represents the standard file format used for additive manufacturing production. It is a triangular representation of a 3D geometry. That means when a CAD model is exported to STL format, the surface is subdivided into a triangular mesh. So each triangular mesh is called as a triangular facet and it is defined by a normal and 3 points representing its vertices. So while the aspect ratio and the orientation of the individual facets is governed by the surface curvature, the size of the facets is driven by the tolerance controlling the quality of the surface and the representation in terms of distance and facets from the surface. The vertices are also listed in counterclockwise direction and the outward normal is the vector that indicates the boundaries of the object, suggesting that the software which is the outer part of the geometry and which is the inner one. Now this is how a facet is generated or STL file is generated. So first there are 3 points and each of these 3 points represents its vertices. Then the aspect ratio and the orientation, like I said, is governed by the curvature of the surface. Then also the size of the facets is driven by the tolerance and the controlling tolerance, and this controls the quality of the facet. Then also the fidelity of the surface is directly proportional to the number of triangles applied. That is, the higher the number of triangles applied, higher is the fidelity. So next we come to the quality of an STL file. Often the quality of an STL file is also determined the quality of the CAD model. Hence there are few steps that are needed to be taken care while 3D modeling and in the end few others while exporting. All these can be summed up and listed in 7 main settings which will determine the quality of the file. So these are the 7 main qualities that are listed below. First we come to angle deviation and chord height. That is, whenever we export an STL file, if the part is rougher or smoother than expected, it is possible to change the angle, deviation and chord height to create the right surface finish. As said before, an excessive faceting is not synonymous of good quality and is of crucial importance that the machine resolution is taken into account while doing the operation. Next we come to surfaces. Surfaces, we need to make sure that the surfaces in the CAD geometry they are not missing or holes or there are presence of holes of any kind on the surfaces. The solid geometry has to be watertight whenever it is exported. Some of the 3D modeling software such as Inventor, SolidWorks or Creo, they produce good solid geometries consistently. Some other softwares based on surface modeling such as Rhino need to be used with more attention. Therefore modeling should also be done with an eye of respect for free edges. Wall thickness. Whenever we are modeling, it should be always be remembered that the STL file works only for solid geometry and not for surface models. Hence, it is necessary that all the walls of the model have a relevant thickness, even if it is very small. Also, the assigned wall thickness should match the resolution that is intended to be used by verifying which one is the minimum feature size that the machine can handle. Next is the normals. As said before, triangular faceting of the surfaces is also described by its normal. The normals are indicators of the direction of the object. With other words, according to the direction of the normal vector that is pointing at the inner surface, inner side and the outer side of the part is defined. Hence, it is optimal in optimal situations. All the normals are pointing outwards. In some cases, whenever there are overlapping surfaces, then the normal is mismatched. Next, whenever we have multiple shells or nested features, the production of multiple parts or parts for assembly can be sometimes problematic. Therefore, it is always a good thing that to save each of the individual part as a separate STL file. Then they will be managed by a technician and then eventually be put together on a same building plate afterwards. The next comes edges. Especially in Rhino, when trimming an object or whenever you create a new one, some edges can be left behind in the model. Be sure that we have to avoid them. They can create confusion during the processing of the file. Next is tab features. The main reason for this is that the outcome will be of overlapping surfaces, and some machines reject this option. For objects with embedded mechanics, it is recommended that to consult the technician to define an optimal solution. Next we come to an interface that links both the CAD system and the rapid prototyping system. First, the main function of the interface is to handle and transfer the data of a given part from a CAD system to RP system. An RP system uses the data from the CAD system to produce a model or a prototype or a part, component or a product. However, an RP system cannot be used directly from the data from a CAD system. The data needs to be converted to a suitable file format so that it can be read and understood only by the rapid prototyping system. So there are basically three steps in producing a prototype on an RP system. First is that a part is modeled on a CAD/CAM system and must be represented as closed surface to enable the system to create the solid object. Next is the solid or surface model is then converted into a file that the RP system can understand. Then the RP system then analyzes the file to generate the commands and to fabricate the model on the rapid prototyping machine. There are two factors that can affect the data integrity and quality of the model produced during the interface between the CAD and the rapid prototyping system. These are the format used to translate the CAD model into a file that the RP understands, and the tessellation process that the file format generated are used. Next we come to the guidelines in data transfer between CAD system and rapid prototyping system. So the guidelines for data transfer are divided into three aspects or three different areas. First is prior to the conversion of the STL file. So steps to be followed before converting a CAD model into an STL file is the CAD model has to be on a positive area of the X and X, Y, Z coordinates. Minimum values of X, Y and Z coordinates should be above 0. The CAD model created should be in a closed solid model. There should be no other elements such as 2D elements in this model. The next step is during the conversion process of the STL files. In the conversion windows, the rapid prototyping system will prompt the user to choose the value of the tolerance. There are two types of tolerances that are involved, that is the adjacency tolerance and the triangle tolerance. The values of tolerances are dependent on the shape and the size of the model. It also depends on the experience and the knowledge of the user. A closer tolerance is recommended as it will accurately approximate the model as compared to a wider tolerance value, but a closer tolerance will also require more triangles and a larger file size. Next is transferring the STL file into the RP system. Once a CAD model is converted into an STL file, it is then sent to an RP system. Before this file is transferred, the following needs to be done. That is, the STL file has to be checked for errors or defects. For any errors that are occurred, the STL file should be repaired and then verified again to ensure that the file is free from error. So now we come to repairing of the data. Computer-aided modeling or computer-aided design are starting point for many downstream applications such as mesh generation, structural, fluid or thermal analysis, or rapid prototyping, numerical controlled machining, casting, computer graphics, etc. Each of these downstream applications are strongly dependent on the accuracy and consistency of the input geometry, but due to numerical problems such as imprecise design, software idiosyncrasies, or data exchange issues, there are some patches that are produced on the CAD step. Efficiency and reliability of modern CAD systems are also dependent upon the tool that are used, and this at present is a topic that is to be researched. And there are also some mathematical issues concerned with the computation, representation and manipulation of the complex geometries. So these are basically the defects that occur in the CAD data. Some they are surface patches, then tolerances which are unpredictable. You can see gap formation and formation of cracks, and on the surface, like I said before, hole initiation must be prevented. Then facets, overlaps, and you can see some kind of T connections, and there is a lot of invalid topology and inconsistent orientation. Now, in order to minimize all these defects, we come up with an algorithm, and this algorithm is known as a repair algorithm. So, firstly, these are the steps that the algorithm follows. First one is opening the information model into the repair tool. That is, it is essential to precisely understand the difference between the geometry and the topology to work with the repair tool. Geometry is a representation of simple shapes which have more mathematical descriptions such as points, curves, etc., which is known, while topology defines the connectivity and associativity of the entities. In this library, objects are topologically represented by entities such as vertex, edge, wire, face, shell, etc. Next is importing and exporting of the file. Importing and exporting module of the algorithm includes the exchange of CAD data between different standards and OCC shape as intermediate data. CAD data are read from neutral frame format and translated into the original shapes. The healed geometries are exported to STL, STP or IGES file formats. Before shape healing or some shape fixing and shape sewing, some useful parameters are extracted from the input model. We will be talking about shape filling later on. These parameters have to help us to have a general knowledge about the input model and consist of a number of entities, a type of entities over all dimensions of the model, IGES, global sections, information, etc. Now we come to shape healing. Once the geometries are imported and translated to the original shapes, the next important work package is the shape healing, which is intended to solve commonly found geometrical and topological inconsistencies in imported CAD format. In this tool, the shape healing package consists of two parts: shape fixing module, which deals with extra intra-entity errors, and sewing module, which is intended to resolve errors between entities and used to ensure the topological connectivity of the model. Now we come to shape fixing. Due to various reasons mentioned in the previous sections, many geometrical or topological inconsistencies might exist in CAD models. Intra-entity inconsistencies imported from CAD model are repaired using shape fix module of the developed tool. Next is sewing. In general, IGS file format is preferred to convey the CAD model into information when it comes to complicated shapes, such as ship hull or car body, etc. This file might have plenty of topological problems with regards to gaps and overlaps, which is a major problem for downstream mesh generators, and then for numerical complications such as CFD and CSD, that is computational fluid dynamics and computational solid dynamics. Here comes the need to repair this inter-entities topological problem to ensure downstream application easier and possible. In this work, most of the problems are solved fully and automatically, and depending on the fact that how corrupted IGL file is with regards to setting the tolerance value. Sewing algorithm is tolerance driven and allows the creation of connected topology. Now we come to a few case studies. The first case study is how regards slicing a 3D CAD model in STL format and the laser path generation, that is the tool path generation. So the process of rapid prototyping is an integrated product manufacturing process without human interference. Product data which has been designed by CAD software is inserted into the program and then directly sent to the rapid prototyping machine, which manufactures the final product by converting a slice of the raw material powder to solid material, then bond it to a previous layer automatically. The program reads the data of 3D design which has been saved in STL file format that requires a decoder for the codes used to store these type of files. The program then displays the design graphically to ensure the form and the dimensions of the model. Then the process of slicing of this model digitally starts from the bottom of the design and then finishes at its highest point. The outer contour line of the slice defines the material of the model. The inner contours define the cavities within the model, and the tool path for the laser beam is generated to cover all the areas that represent this material area. The tool path is used to generate instruction codes sent to the laser source, which controls the direction of the laser beam, which then converts the laser raw material powder into a solid final product. Now this is the slicing algorithm which is used to slice the geometry by the STL file. Slicing the geometry requires the data from bottom to top. So these following steps are followed in order to slice the layers accordingly. So first one is to find the cutting plane. The program scans the STL file, picks the Z coordinate of the faces, compares it, and finds the top and bottom of the geometry and adds the layer thickness. The next one is find the faces that intersect the cutting plane. So the program scans STL file to pick on one facet at a time. The Z coordinate of its 3 vertices are compared with the height of the current plane. Next one is to find the before the third step, the program slices the facet accordingly to 7 possible cases, which are divided into 5 groups. So each group, there are 5 groups mainly. Like at the first group, all vertices may be away from the cutting plane. Then the second one point is in the cutting plane with the 2 remaining vertices in different regions. Third group is 1 point in the cutting plane with 2 remaining vertices can be above or below the cutting plane. And the fourth one is 2 vertices lie in the cutting plane and the remaining vertex can be above or below the cutting plane. And then all 3 vertices can be in the same cutting plane. So this is more of permutation and combination. The third step is finding the lines that intersect with the cutting plane. I'm sorry, we have done with that. The next step is find the coordinates of the intersection. So for each of these lines, we will find out the x and y coordinates of the points where the edge is intersected by the slicing plane. By connecting the intersection points in each triangle, a set of straight line will be formed. Next is contour construction. Contours are closed polygons that do not intersect with each other. There will be the start and the end vertices of a line, and this is called head and tail of the line respectively. The position of the head for one line is the same position of the tail for the neighboring line. So contour construction follows its own algorithm. We will not be going into detail for that. Contour filling is also one of the most common problems in graphics and picture analysis, as in rapid prototyping, where the contour is defined in a polygon. The interior region of the polygon has to be found. So now we come to the second case study. Previously we saw what slicing algorithm is and how a laser toolpath is generated. So in this we will be seeing the evaluation of the shape complexity based on STL data. Then in this for a case study, I noticed that it presents part complexity based on basic information of the STL data and a few methods of evaluating the complexity of the shape based on the parts of the STL data. Methods vary from very simple based on the number of triangles in STL file and parts volume to the more complex mathematical determination based on relations of basic STL data. It is found that the evaluation of complexity is based on only the basic data of STL, which gives only a basic view on part complexity. The complexity of the shape of a part is an important factor for all manufacturing procedures. Whenever conventional machining is used, parts complexity presents a key factor in determining the optimal way of manufacturing. Also, whenever rapid tooling is used, for example silicone rubber molding, the complexity of the part determines the parting plane layout and eventual tool construction such as inserts, cores, etc. Even when using certain rapid prototyping procedures, the support material consumption depends highly on the complexity of the part, and together the problem of optimal orientation and the position of the part significantly influences the manufacturing cost. Choosing maximum efficient manufacturing processes on the base of the part complexity is a new perspective in manufacturing, which properly evolved and compiled can cause revolution in manufacturing optimization, especially in hybrid manufacturing processes. So these are the different types of evaluation methods are different methods of evaluation based on number of triangles, based on the ratio between volume and number of triangles, ratio between the path, volume and surface, minimal parts, volume and the block. In this study they have used 6 parts, basically a prism, rib, a plug, housing, holder and wheels. So the first one is evaluation based on the number of triangles. A very rough evaluation of parts shape complexity can be made by examining the parts file size, which depends on the number of triangles used. The size is very closely related to the number of triangles used to describe the part in the STL file. The file size or number of triangles depend on only the parts complexity and the exporting the resolution, but then are not influenced by the part size and therefore can be used for a rough evaluation of shape complexity. The first figure shows the left top corner shows that the comparison between the ASCII file or bin file size and the number of triangles used, that are the number of triangles that are generated. So the next one is based on the ratio, evaluation of part complexity based on the ratio between volume and the number of triangles. Number of triangles can be established with the appropriate software. Determining the volume can be made into 2 ways. The precise determination of the volume can be made according to the known algorithm. Also, the ratio can be determined with a rough estimate for the volume based on the minimal block volume that can accommodate the part. When the part is optimally oriented, the minimal block volume can be determined by searching for maximum and minimal values of the triangle coordinates in each of the axes. So this shows it. As you can see, for the rib, the volume to parts ratio is very high. So the third method will be evaluation of shape complexity based on the ratio between parts volume and the surface. So this is a comparison, the left bottom corner. Another evaluation of shape complexity based on STL data can be made based on the volume or surface ratio. Calculations are made for both the exact volume and the block volume. Volume to surface ratio basically describes the quantity of curved or free-form surfaces in a part. It also points the difference between thin-walled and bulked parts. Then finally we come to evaluation of shape complexity based on the ratio between a minimal block volume and a part's volume. So this is the again comparison due to the minimum bulk volume and volume ratio. So here block volume or volume ratio also shows a difference between simple bulk parts and more complex preform surface parts, and can be comparable to both volume or surface ratios. So I have given the paper which I have referred for both the case studies. You can go through it if you need it in more detail. So finally I'm going to conclude this presentation saying what I've done. Initially we saw a brief description of the STL file, then later the methods of representation of the STL facets are seen, that is triangular facet and how it is represented, like the 3 vertices named in counterclockwise direction and the normal facing outward. The factors that are used in determination of the quality of the STL file is observed, and the variation in quality is seen. So also the link or the interface between the CAD and rapid prototyping system is the main component for the transfer of CAD data into the RP system. The guidelines for data transfer through the interface are also studied, and this gives an insight as to how to minimize the errors. All the different problems occurring in data and algorithm for repairing the data is also seen. From the first case study, a new approach for the model slicing is seen, that is along with the generation of laser path, and finally evaluation of the part complexity using various methods was seen. So thank you. If you have any question, please post your comments below.